last week we discussed about the classification of the properties. Okay, it can be divided into primary. Okay, generally is the single value properties, and also secondary properties. Okay, to use these properties, we have to get the information also is redundant with the primary properties. Okay, where's the slide? And functional properties. Okay, so it's depending on the intensive variables of the temperature, pressure, as well as the composition. Similarly, also for the mixing. Okay, is the additional of the structure information. Okay, depending also on the intensive variables, pressure, temperature, as well as the composition as well. Yeah. So, and as we move on the relationship among the properties, okay, properties models, and then what else? Uh, uh, Solvers and then calculation algorithms. Okay, so we discuss about that one. So, for example, if we want to determine the primary and secondary functions, we need the property models, such as like SRK, MG, okay, Unifex. So that is the property models, as well as if you want to determine the phase behavior for the VLE, LLE, as well as SLA by using the calculation algorithms. So you need a numerical solver, right? So and then we focus more on the primary properties. Okay. So this is we employ on the structure variables. Okay. For example, we use MG method. Okay. NG method is a simple, accurate, as well as they have extensive group parameters. Okay. For the properties and also molecules. Okay, if you remember F theta equal to summation of NiCi. Okay, if you just consider FiCi is for the first order is enough. For the maybe for the monofunction. Okay, if involve the polyfunction of the compounds. Okay, so you have to use second order and third order, and F theta will be summation of NiCi plus summation of NJDJ as well plus EK and 0K or OK. Right. So property model is important. This is a primary step. Okay. So the definition of F theta. Okay, what you have to use. For example, you want to determine the normal volume point or normal melting points, and then you have to also substitute the F theta with the what is it, the equation, for example, exponent T divided by TB divided by TBC for the normal volume point, and as you can calculate by using on the right side of the equation. Okay. Okay. So also we already show you the examples. And today we will discuss about the secondary properties, functional as well as mixture blend. Okay. Uh, Still under the property prediction. Okay, just we discuss more details. Okay, brief and details about the property prediction before we move to CMD problem formulation as well as the software. Okay. So secondary properties actually is the other properties that we need to consider after the primary. Right. Uh, there are actually is if you remember the relationship between the property models, properties, calculated values, calculated properties values. So this is a consistent. Okay, with that figure. Okay, in the previous step. And it consists of three steps that you need to specify the properties before for the estimation. Okay, what you have to do is first step is select an estimation method and property model for the specific properties. Okay, and then second is to identify the properties data. Okay, that you need to use the model and verify the application range. Okay, of the estimation method for the chemical species of the specific type, and the third is a retrieve from the database or predict the necessary properties. This is you're going to use for the input. So let's see the example. Okay, for example, this one. Okay, estimate the Hildebrand solubility. If you look at here, that the Hildebrand solubility is the symbol is delta T. Okay, for the acetic acid ethyl ester. This one is from the smile. Okay, the symbol for the acetic acid ethyl. So T theta, the equation is 1000, okay, times with delta H evaporation minus 8.314 times with 298, okay, Kelvin divided by Vm. Okay, so heat of evaporation is delta Hv, okay, and then is the molar liquid is Vm at 298 Kelvin. So how you determine these secondary properties? You need the delta from the, is it this one, H vapor. How we can get this one? So we have to get from the primary properties. Okay, primary properties. Okay, which is you calculate in the previous previous example, or is shown in the previous example. Okay, this one for example. Okay, you can calculate from here. Where's the f theta? Ah, yeah, this one. Okay, so this is a you need the primary properties. So we look at here that this one is the heat of vaporization. So you need that input from the heat of vaporization. Okay. Okay. Also, you can calculate how to calculate the heat of evaporation. If you remember from the what is it, from the chemical engineering thermodynamics, how do you calculate the delta H vaporization? Okay. So I hope you can still remember in chapter 4. Okay. So you need that knowledge. Okay. So after you substitute delta H with the value. Okay. So actually this one is just determined from the CAPEC database. Okay, just substitute. So we can calculate the Hildebrand solubility. Okay, about 18.23 megapascal. Okay, this is the parameter. Okay, so for another example is the refractive index and critical compressibility factor. If you remember what is the compressibility factor, okay. Actually, if the model is PV equal to ZRT, if you remember, okay. But in terms of critical, PCVC, okay, uh, uh, divide by RTC, so you can get C, okay, as well as the refractive index. So what you have to do, since you already calculate the if you calculate, but this one is for example is for bifinance, but for if you use the previous examples, okay, delta T you can substitute into this equation so that you can get the answer for the refractive index. However, for the compressibility factor, if you remember this equation, okay, PV, okay, equal to NZRT, okay, or equal to ZRT, okay. So just rearrange these ones in terms of Z. So P V equal to RT. Okay. So just substitute all the information you can get from maybe from the data. Okay, or from the database, CAPEC database. To substitute you can get compressibility factor. Okay, this is a critical compressibility factor. Okay. So I think this is mostly is you need the knowledge of chemical engineering thermodynamics. Right. Okay, this is another example for the polymer repeating units. Okay, for example, this one CH2, CH2, CHCl. Okay, estimate the solubility parameter. Similarly, also delta T from the CAPEC properties. Okay, CE divided by VA. So just substitute. Actually, CAPEC is the database. Okay, if you ask what is the CAPEC property prediction software, this one. So just substitute, you can get delta T. Okay, so this is how you calculate. Okay, generally it's redundant with the primary properties. Okay, so all those are example for the secondary properties. Right. Okay. Any question about the secondary? Okay, if no questions, let's we move to the
No, Ratan.
okay. Let's we move to the step in the functional properties. Okay. So as I told you, is as a function of the temperature, pressure, as well as the composition. Okay, but mainly is a function of the temperature, and some is in case some case is a function of pressure actually. Okay, so if you have a properties that properties of the you interest that one of the properties, so you have to follow this three step. What you have to do is check a database for the availability, okay, for the correlation. Okay, for example, if you have a database, you have to construct a graph so that you can predict the properties. For example, the properties such as what is it, the saturated vapor or vapor pressure, or maybe like liquid density along with the temperature. So what is the functional properties of that target compound? Okay. And second, if available, use the corresponding correlation, right? And then if not possible, okay, use a model based on the principal corresponding state. This is in the thermodynamic. Okay. If available for the necessary properties, otherwise you have to collect experimental data. So you have to use some experiment, okay, so that you can do the correlation, right? So this is the example, okay. So what you have to do is the problem is determine the vapor pressure and liquid density as a function of temperature, okay. So you have to predict this vapor pressure and the liquid density for the acetic acid ethyl ester. Okay. So if we check in the CAPEC database, okay, this is from the software for the correlation. Okay, for the vapor pressure, liquid density, and this one is P saturated, right? Antoine equation, if you still remember, in the chemical engineering thermodynamics to calculate the vapor pressure. You still remember, right? How to calculate? You have to determine the parameter A, B, C, and also C. And then similarly, also for the liquid density. Okay, you have to determine A, B, C, as well as D. Okay, this one is generally there's available in the database. Okay, and what you have to do is you have to construct the graph so that we can predict along with the temperature. Okay, so from this ones, along with the temperature, for example, starting from the what temperature, from room temperature, okay, or 20 degrees C, 25 degrees C, until what temperature? Maybe 50 degrees C or 100 degrees C. So we can see the correlation for the vapor pressure and liquid density with the temperature. Okay. Okay, so this is the example once you substitute all the parameter into the equations. Okay, so we can get the vapor pressure against with the temperature. Okay, so here at for example 40 degrees, right? So we can predict the vapor pressure is about 25 kilopascal. Okay, and increasing the temperature, so increase in the vapor pressure. How about the liquid density? Once you increase the temperature, the liquid density is actually is reduced linearly. Okay, for the ethyl acetate, okay, or acid ethyl ester. Okay, so we can predict that rather than you do all the experiment for each temperature, right? So you can do this one by using the software. Okay. So this is for the functional properties. Okay. So for the model functional properties, okay. So this is the guideline that you have to follow to employ the correlations for the functional properties. So what you have to do is always check the correlation limit and extrapolations beyond the limits, and always check okay whether sufficient accuracy, and also you if the correlation is not available, so you can check or estimate with the experimental data, and then you have to do cross validation. So if possible, okay, generally if you do cross validations, you can get the accurate answer. Okay, how much the error, right? Generally after the screening. Okay, we're not gonna do all the experiments. Okay, so that is for the functional properties and the example. So any questions? So we already covered about the primary okay properties, secondary properties, as well as the functional properties. Okay, so let's we move to the mixture properties. Okay, what is the model? Okay, generally for the mixture properties, if you remember, we deal with the vapor liquid equilibriums, okay, liquid liquid equilibriums, as well as solid liquid equilibriums. If you still remember vapor liquid equilibriums, what's the equation of the vapor liquid equilibriums? The fugacity is going to be similar, right? Okay, the gives energy in vapor as well as in vapor and liquid is similar. Okay, and the fugacity is similar. Okay, do you still remember? For example, what is it? Xi gamma I. Okay. What is it? FIL. Okay, equal to YI uh, Phi times with the what is it? Pi, right? Okay, if you still remember. That is the properties for the VLE, which is in equilibrium. Okay, I hope that you can still remember how to determine the activity coefficient. What else? Activity coefficient and fugacity coefficients. Is it still remember how to determine a gamma I? Anyone still remember how to determine the gamma I? Phi, fugacity coefficient, activity coefficient, fugacity coefficient, activity coefficient and fugacity coefficient. Yes. Do you remember how to determine the activity coefficient, fugacity coefficient? Anyone? Alif, you still remember? For VLE. I'm not sure for LLE and SLE. I think you learned already in the mass balance and energy balance, or maybe in the suppression process. But for the chemical engineering thermodynamics, yeah, actually that is the course that I teach. Who's last time in my class? Huh? Alif, right? Alif, are you in my class last time? Do you remember? Alif, are you in my class last time? Or the chemical engineering thermodynamics? No response. What? How to determine the activity coefficient? Anyone? What? Anas Hakimi. Anas Hakimi, you still remember? Activity coefficient.
No, doktor.
Why no?
Uh, Tengah baca note ni.
Dia tak ada
Buka BL.
tak ada dalam slide ni.
Tak. Tengok dalam BLE punya note. Okay.
Apa yang you remember? Chapter 12. Augustus, chapter 11. You still remember?
No, doktor. Itu
Anyone? Macam mana ni? dia punya
Need to
motif
do
lah.
some revision, I think.
Revision.
Yeah.
Okay. So if you still remember, we use the Wilson equation, Univac. What else? What else, Wilson? Another Wilson and then Uniquark. Right. You still remember that Wilson, Venla,
Lee Kessler lah.
Lee Kessler. Daripada information of Lee Kessler itu chapter 3, chapter 6 kan, tapi information of Lee Kessler daripada Lee Kessler tu you boleh dapatkan ni Fugacity coefficient kan. Ingat tak itu chapter 11? Takkan tak ingat? Aduh.
Baik.
Still remember. Okay. That's important for VLE actually. Okay, because you must remember that we are not deal with the ideal fluid. Okay, it should be have for the mixture should have, for example, liquid. It should be have a activity coefficient. If ideal, yes, become 1. Okay, remember right? Modified Rock's law. What is the condition? Okay, in liquid as well as vapor. So you have to remember that. How do you predict the activity coefficient? And also, activity coefficient. Okay, and then you do the prediction with the Wilson, Venla, something like that. You still remember, right? Maybe, yeah. I hope you can still remember. Okay, this doesn't matter, but just make some brief through to the chemical engineering thermodynamics. I think that is important, especially VLE. Okay, VLE, that is important. I'm not sure for LLE and SLE because I never teach this kind of the subject. I think you learn in the separation process as well as mass balance or energy balance. Okay. Okay. So the commonly that we encounter in the what is it the chemical based product design is, of course, is the functional properties of the mixture. Okay. For example, is the bulk density or enthalpy of the mixture, if you still remember. And they have an enthalpy of the mixture excess properties, right? Something like that. And then phase equilibriums, okay, that related with the properties of the compound, such as like liquid phase activity, okay, saturation temperature, bubble point, and dew point temperature. You still remember, right, this one, bubble point and dew point, how to determine in chapter 10. So I hope that you can remember this one. This is a phase equilibrium, definitely. Bubble point, dew point, flash point. Okay. So to calculate that this mixture properties, okay, definitely you need the pure mixture pure component properties, okay, with the calculation algorithm and equation. That's why when we learn a chemical engineering thermodynamics, we learn about the pure component first before we jump into or before we proceed with the mixture, because we need the information of the pure component. We want to know the behavior, the basis. Okay. Okay. So for the functional mixture properties, okay, for the compound and the composition in the mixture are unknown. Okay. Together with the phase identity. Okay, this one. And then if at non-temperature pure compound properties, this one theta I, generally I is for that particular component. For each compound we need to estimate. Okay. And then by using a mixing rule, okay, bulk properties of the mixture, theta M. M is for the mixture. So theta M is equal to theta naught plus theta E. Or naught is a theta is for the ideal. Generally we use if previous we use what is it? M mm equal to mig plus me, right? E is for the excess mixing properties, right? So if you still remember, okay. So if the excess mixing terms, this one we neglect. So theta m is equal to theta ig, or ideal, not ig, it's ideal, id. Okay. So this is a molar average of the pure component properties. Okay. So it should be times with the xi, with the fraction, with the summation of the theta I xi. Okay. This is for the pure component. Okay. So actually is the vary with the properties and the specification. Okay, so that is for the functional properties mixture. So how about the equilibrium based mixture? This is what I told you about the mixing, okay, two or more phases in equilibrium, such as like VLE, LLE as well as SLE. This is the criteria for the isofugacity. Okay, general equation, if you still remember. Okay, this is general equation. This is what I told you. Okay, okay, this is the fugacity, right? Okay, and this one is a P. This is in vapor. This one is liquid. This one in vapor. This we have to remember. So with fugacity, each phase is similar, liquid and vapor. Okay, this one LLE similarly also, since in equilibrium. Okay, so you have to remember all this equation. This is the basic that you already learned previously. Okay, and the definition of each symbol. I think I just take one example for the VLE. This one. Okay, since I teach chemical thermodynamics. So gamma I, remember activity coefficient, how to determine Wilson, Venla, and so on. In fact, but mostly if you use the software, yeah, maybe we like combination effect and unique quark. Okay, fugacity coefficient. This one, if you remember, Phi. Okay, of the compound I in vapor. Pi saturated is a vapor pressure of the compound, pure compound. Right. This one is the total pressure. Okay, and Si is the fraction. Okay, this one in liquid and this one in gas. Yeah, you remember, right? So VLE is important, especially is starting from for the mixture blends or for the chemical engineering thermodynamics, starting from chapter 11, 12, 10, that one. Okay, so I hope you can go through. Okay, in brief, for the chemical engineering thermodynamics. Okay, that is the basis. Okay, so for the phase equilibriums, okay, problems, okay, we involve to face the appropriate fugacity question is we selected, okay, together with the mass balance as well as a mole fraction summation, so we can solve by appropriate solver or software. Okay, what we're gonna solve is like VLE, right? We can get the bubble point, dew points, okay, and then LLE, amount composition, and SLE, saturation temperature curve, solidity, and solid in the solvent. So I hope you can still know how to determine this one, bubble point. Okay, dew point. You still remember how you do the K value? You have to get the K value. Okay, right. You have to guess and do the iteration, trial and error before you get the, for example, you want to determine temperature, right? Okay, based on the K value and pressure, so you can get the K value, the actual K value. Okay, still remember chapter 10. Okay, please refer chemical engineering thermodynamics. So this one, Mead and Vanes. Okay, so and for the last, this is the example of the specification needed, the properties as well as the property model parameters for the two phase equilibriums. For example, if the specification needed for the problem if unifact activity coefficient, unity, and also composition, right? Bubble point. If you still remember how to calculate bubble points, the specification needed is a pressure and as well as the composition. Okay. This one, what you have TC, PC, omega, P saturated. Model property is excess Gibbs energy, and the output is going to be activity coefficient, because our problem is we want to calculate the activity coefficient. Okay, so this one is chapter 12 to remember how to determine. Okay, bubble point, T bubble. Okay, this one is chapter 10. Okay, this one I think it's more to liquid and solid. I'm not sure this one. Okay, but similarly also I think heat of fusion, melting temperature. Melting temperature is related with the solid as well as liquid, of course, rather than TB. TB is more to liquid and vapor. Okay. So this one left hand side equation 4.7. So that's mean if you remember f theta. Okay. So you have to use that equation so that you can calculate. And this one is as the output. Okay. Any question about this one? Okay, very short. We just finished the properties prediction. Okay, next week I think we're gonna focus on this one. This one, and also this one. Okay, question of which and some case study how to design this one. I'm not sure for the software that we're gonna use. Maybe it's a iCast. Any question? No. Okay. If no question, so we stop here. Anyone already submit the assignment? Do you need an extension of the deadline? Activity 6, I think, for the property primary. Any questions?
No question.
Okay. I heard already is clearly understand. Yes, Dr. Wood assignment. Dr. Wood to what is it? Assignment downtown. Okay. Yes, Dr. Wood assignment. Okay. Okay, thank you very much for today. So, again next week. Thank you guys. See you again.
Doktor, saya tak pasang attendance.
Attendance.
Thank you,
Okay.
Doctor.
Okay.
Kata you tahu.